Alright, so now for the last video in the conic definition series. In this video, we'll be going over just the technical definition of a hyperbola, like why it is the shape that it is, and some important features of a hyperbola, like its foci, its directrices, and its latus rectums. So first off, the technical definition of a hyperbola, well, actually not yet, but how does a hyperbola form? Just like every other conic section, if you remember from the other videos, a hyperbola forms when a plane intersects a double-napped cone. This is the amazing illustration of a double-napped cone. And the special thing about a hyperbola is that the plane has to intersect the cone at an angle that is perpendicular to the bases and also parallel to the axis of the cone, which is right there. So it has to intersect at this angle, and then when it does, the cross sections will form this shape, which, as you know, or at least as you should know if you're watching this video, is the shape of hyperbola. Pretend that's like actually lined up. But yeah, it's the shape of a hyperbola. All right, so what is a hyperbola? Like, what is the technical definition? So a hyperbola, like every other conic section, also has two foci, and they are inside of the arc, just like as they would be in a parabola. And what a hyperbola actually is, it's the locus of points, so it's all the points for which the difference of their distances to the foci is constant. And that might be a little confusing, so just to unpack that, what that means is, like, say if I have a point, actually I'll go back to it using white. Let's say I have a point P. This distance, the distance from P to this focus, let's call this one, let's say A, and this is focus B. And then this distance, AP minus PB, that is always going to be constant, like even as this point travels up the hyperbola. So for example, for this point, let's say right there, we'll call this Q, QA minus QB is going to be the same amount because that difference of distances from the foci always remains constant, which is pretty cool and it's pretty important. So that's the technical definition of hyperbola. Remember, the difference of the distances between 2 points must be constant. And if you remember, this is the kind of opposite of an ellipse in which the sum remains constant. And now you might be thinking, well, how do I find where these foci are in the hyperbola? And let me show you that right now. And I can show you this with a horizontal hyperbola because it works the same way. Actually, no, just for sake of consistency, let's use vertical. So we have our hyperbola right here. Oh my goodness. Let me zoom in. Okay. And then, I'm so sorry. I really can't draw. You know what? Whatever. This is good enough. Okay, so we have our focus. Those are the 2 points I drew in earlier. And then some other important points are the vertices. The vertices are right, like if you were to imagine a hyperbola as two different parabolas, which it's not, but if you were to, these vertices would be on the same spot. And so these are your vertices, and then this length right here, this is the center right in the middle of the vertices. So this length right here is going to be A. And then this length, maybe I should do it in highlighter. Yeah, this length in highlighter, that is going to be C. C. Oh, wow. Okay, that doesn't look great, but whatever. That's C. And then there's another value because there's also two other points right here, and these are called the co-vertices. And then the length from one of those to the center is called B. And so A and B are important in determining like the equation of the asymptotes of the hyperbola and stuff like that. And then there's also a very special relationship between A, B, and C, just like how there is in an ellipse, except this time the relationship is the Pythagorean theorem. A squared plus B squared equals C squared, which is definitely nicer than, and just more easy to remember than the equation, the relationship for ellipses. What's something else I guess that you should know is that 2b, so this length, like this, 2b, that is called the, that's called the conjugate axis. I cannot spell either, apparently. Conjugate axis. Think maybe like co-vertices, conjugate, CC. And then 2A, this is called the transverse axis. It's the main axis. So it's the one that connects the two vertices. What else? Oh yeah, hyperbolas also have directrices. So I'll draw this down here. Just like how every other conic section has a directrix. So we have our two foci in here, and then just like in a parabola, the directrices are going to be outside of the arc. And if you recall, ellipses had two directrices, one for each focus, and that's exactly how it is for hyperbola as well. There is going to be one directrix that corresponds with each focus. And there's actually another important relationship between the hyperbola and the focus and the directrix, which I will tell you just right now. So for every point on this hyperbola, let's say this point P again, there's going to be a very specific ratio of distance from the focus and the directrix and its corresponding directrix. So like from here to here, the distance, the ratio of those two distances is going to be the same as the ratio of these two distances from Q. So like for example, let's say this is 3 and then this is 2. This distance is going to be 6 and this distance is going to be 4. And obviously I didn't draw it really well to scale, but there's going to be that common ratio, which is important. That's really important. Another really important thing is that that ratio, for example, is only going to be constant. Like let's say we have a point here. I can't use this focus and then assume that the ratio with the distance from P to the opposite directrix, like till here, is going to be the same. It has to be the corresponding directrix for each focus. Or if it was for this focus, it'd got to be that directrix. But that ratio is always going to be the same. In this case, it would be 3/2. And that, if you recall from the earlier videos, like the one about ellipses in particular, that is called eccentricity, the ratio of the distance to the focus over the distance to the directrix. And for hyperbolas, the eccentricity is always going to be greater than 1. You know, like this is 3/2 is greater than 1. And that's also really important because you can, now that you've seen, hopefully, I have another video on ellipses and circles and parabolas, but hopefully if you've seen that, you should know that the eccentricity for an ellipse is got to be less than 1. The eccentricity for a parabola is 1, and the eccentricity for a hyperbola is greater than 1. So if you know what the eccentricity of a conic is, you can identify that conic, which is super helpful. But anyway, how do you find the equation of this lattice rectum? Sorry, did I say lattice rectum? I meant directrix. But it's actually, in any case, it's actually the same as the how you'd find the directrix in an ellipse. So like let's say this was the center. The x-coordinate in this case, because it's the x-coordinate that's shifting, it's a vertical line because it's a horizontal hyperbola. For this one would be plus a over e to the x-coordinate, which eccentricity, e for eccentricity, is also equal to c over a. So you could also write that as a squared over c to the right. And then, as I'm sure you can guess, the equation, or however you get to this directrix, is by taking the equation of the center, the x-coordinate of the center, and shifting it a squared over c to the left, which is the same as you do if you were to find the directrix of an ellipse. Now, one thing is kind of interesting if you note, this might make it easier to remember, that to find the directrix, and this is from the center, you shift by A over E. And if you recall, for the focus, this distance is C. But if E is equal to C over A, then, well, if we multiply both sides of this equation by A, we get AE equals C. So that means that the distance to the focus is actually just AE. So if you want to find the distance to the focus, that's AE, like A times E, and the distance to the directrix is A divided by E, which might help you remember. It might not, but in any case, it's just interesting and it's good to know. Okay, so the last thing I think we should go over, look at this pretty drawings. The last thing I think we should go over are the lattice rectums of a hyperbola. And those, I hope you know by now, are lattice rectums are chords that go through the focus of a conic, which in case our focus would be here. They also are perpendicular to the major axis, which in our case would be the transverse axis. So they're perpendicular to that, and then their endpoints both endpoints touch the conic. So that would be these lines right here, these line segments. Those would be the lattice rectums of a hyperbola. So as you can see, the x-coordinate of this lattice rectum is always, like this entire thing, it's always going to be, assuming the center, this is relative to the center, it's always going to be negative C for the left one, and it's always going to be positive C for the right one, because again, the y-coordinate isn't changing, it's this entire segment here, and we're just going C an x distance of C away, because it goes through the focus. Now, of course, if we had a vertical hyperbola, that would just mean that the y distance changes by C, right? But yeah, now what about the endpoints? Well, usually what I would do is, since we know that the equation of hyperbola is x minus h squared, at least for a horizontal hyperbola, I'm just going to write the equation for a horizontal hyperbola. It's x minus h squared over a squared minus y minus k squared over b squared equals 1. You should know that because this isn't basic hyperbola stuff that I'm going over right now, and you should know the basics before watching it. But so where was I going with this? I genuinely do not. Oh, okay, yeah, I was saying that if I were to find the endpoints of the lattice rectum, I would just take the x-coordinate of the lattice rectum and I'd plug it in and I'd just solve for the y-coordinate. But if you need to know it off the top of your head, or you need to know it fast for team round or ciphering or some other competition, you should know, you should remember that the y-coordinate, or at least the endpoint, is going to be plus 2b squared over a. It's going to be plus b squared over a for the higher coordinate, and then minus b squared over a for this bottom endpoint. And that means the length of the hyperbola, the length of the lattice rectum, and I cannot spell. Length? No, what? What? It's midnight, please cut me some slack. Length. That doesn't look right. Let me write it on paper. I think that's right. Okay, well, if it's wrong, don't come at me. The whole length of the lattice rectum is 2b squared over a. And so yeah, we covered a lot. I threw a lot of information at you, but hopefully it was useful in some way. If you don't get it right now, just revisit it. I just tried to condense everything and put it in one place. And if nothing else, at least looking at all of this, just hopefully it makes you happy. It makes me happy. Look at it. It's so pretty. Yeah, math. Okay, bye.